c'est un plaisir d'accueillir Karl FRISTON à Montréal. Il est neuroscientifique théorique, autorité en matière d'imagerie cérébrale. Il a inventé la cartographie paramétrique statistique qui s'appelle SPM, la morphométrie basée sur les voxels, VBM, et la modélisation causale dynamique, DCM. Ses contributions mathématiques comprennent des procédures laplaciennes variationnelles et un filtrage généralisé pour l'inversion hiérarchique du modèle Bayesian. Karl travaille actuellement sur les modèles d'intégration fonctionnelle dans le cerveau humain et sur les principes qui sous-entendent les interactions neuronales. Sa contribution principale à la neurobiologie théorique est un principe d'énergie libre pour l'action de la perception et l'inférence active. Sa conférence s'appelle « Inférence active et curiosité artificielle ». I'm happy to welcome Karl FRISTON to speak in Montreal. His topic is active inference and artificial curiosity. And with that, I pass the mantle to Professor FRISTON. Go ahead.
Well, thank you very much for that lovely introduction, which I don't even understand French now. We were talking before. I used to do French when I was about 18, but it's been such a long time since I've heard it spoken so fluently. It's a great pleasure to be here. Thank you very much for inviting me. I'm going to spend the next hopefully slightly less than an hour, delivering a talk which I haven't delivered for some time. It's one of my favorite talks, but it's also one of the most difficult talks I give. And it's difficult for two reasons. One, it tries to provide an overview of many different levels of how we make sense of the world, and in particular, how we sample that world to enable that sense making. And I'm going to take the perspective of Bayesian, the Bayesian brain, or the principles of Bayesian inference as the backdrop to try and cover and bring together different levels of optimal sense making and action. So I'm going to be talking about active inference and self-evidencing, and I'll explain what I mean by self-evidencing in a technical way, with a special focus on generative models and active inference, a nod to the fact that our inference depends upon the way that we gather data, and that has a quintessentially inactive aspect. And I'm going to distinguish between inference about states of affairs that we have to make sense of in the moment, and learning the structure of the world and sampling it in a way that responds to epistemic affordances, in particular things like salience and novelty. And the final level that I want to address is not so much about inferring states of the world or learning the structure of the model of the world, but actually identifying the very structure of the model itself, the number of, say, levels in a factorial model, the depth of a hierarchically deep model. So those are the three levels I'm going to try and cover as gracefully and intuitively as possible, although I will spend a bit of time trying to give you a sense and a feel for the underlying mathematical principles that we're appealing to. In summary then, inferring states of the world, learning model parameters, and learning model structure. The second reason this is a difficult talk to give, especially online, is that I want to start by playing a game with you. I'm going to ask you to try and solve a problem, which we're then going to use to see if we can simulate, using these Bayesian principles, the same kind of solution in silico. So I'm going to create a little agent that's trying to solve exactly the same problem. I should have said in terms of people asking questions halfway through, I should have forewarned you about this. I'm going to ask you some questions now, if that's okay. The idea here is we're going to play a game, and I want to know how base optimal we are as people, and how many bits of data or data points are required before we can arrive at a particular explanation for the way that our sensations and cues are generated. So here's the game. It's an abstract rule learning game. So the idea is that you have to identify a particular rule. And I'm going to give you your task instructions, namely your prior beliefs. So the idea is that you're going to choose the correct color based on the arrangement of these three circles here. And the location of the correct color, say the correct color was red, depends upon the color of the upper circle. So this is the important cue here. The color of this central or upper circle tells you the correct color to respond to. And that's all you know. And I'm going to give you a series of examples, and then I'll tell you what the correct color was. And on the basis of these series of data points, I want you to see if you can identify the underlying rule. And I'll have to pick on somebody to answer the questions if I don't have any volunteers. But we'll go through this slowly, and I'm going to go through it slowly for a very particular reason, which will be clearer at the end of the presentation. So we're going to have a series of trials. Each of these is one data point or one play of the game. And I'm hoping that you'll be able to accrue information about the correct choices until at some point, as we work through these games here, you will discover the rule. So let's just start with the first game. Ignore the three colors at the bottom. I've given you the answer there, my apologies. Ignore the three, these three smaller dots are just to enable me to tell you what the correct answer was and for you to remember what the correct answer was for this particular game. So let's just start with this game here. Does Stefan, would you like to guess what's the correct color with this arrangement here? You're muted, and I can't lip read it.
Yeah, I haven't the faintest idea. I'm not to look at the solution at the bottom, I suppose.
Well, yes, you could not derive the solution until I've given you all the answers, and unless you've got the next slide at hand. So you're absolutely right. You have no idea. So you're going to have to guess in the first instance.
Okay, let's start with green.
Well, you're absolutely right, sir. Well done. So.
Yeah.
Have another go. Let's do this one here. So now when blue is at the center, the correct color is green. In this instance, the red is at the center. What do you think the correct color is going to be?
I'm leaning towards green again.
Okay. You're absolutely right. That's quite remarkable. Do you want to?
I'm withdrawing. I'm going to ask somebody else to pinch hit for me because I have too many things to do at the same time here.
Then please choose somebody to. In fact, perhaps you could invite anybody at a point they think that they have seen a rule, whether it's a silly rule or possibly the correct rule, just to volunteer, just to get a sense of how many data points that people have before they start to have hypotheses about what's going on here.
Can I do a show of? Could you put up your hand if you're willing to be consulted for this during the procedure? Just use the reaction. Okay, good. So Pierre is ready to do it. Jacob is ready to do it. Pauline is ready to do it. Very good. Show now, Karl. Do you prefer to stick for a while with one, or just let them raise their hands when they want to do it?
Anybody should raise their hands when they want to do it, and especially if they think they've spotted the rule. But Pauline, why don't you have a go at this one? So red is on top. What is the correct color?
Green again.
No, interesting answer. I hadn't realized this when these were actually generated randomly, but of course there's only red to choose from, so one can sort of guess that it had to be red there. Do you want to have another go? Now green is at the top. What do you think is going to happen now?
If green is at the top, well, then I don't think green should be the correct answer. Red?
Let's just see if you're right. Oh, I'm sorry.
I'm not good at this. I'm sorry.
Yes, I should say it's absolutely impossible to get the right answer at this stage. It's mathematically impossible for you to be correct at this stage.
Okay, I'm reassured.
At some point, you might see what's going on. So again, everybody, just keep on looking and see if anybody can spot a rule. Would you, Pierre? Would you like to have a go? What do you think is the correct color here?
I would say green.
You would say green, would you? Oh, that's very clever. Do you have a reason for saying green?
Well, I guess if blue is at the top, it's the color of the bottom right button. If red is at the top, it's the color of the bottom left button. And if green is at the top, it's green all the time.
Excellent. Okay, that was quite remarkable. So that's the game over, I'm afraid. Pierre has just answered it and found the solution. So I didn't realize this again until Rita Hari spotted this, but it's a little bit political. So if you've got red at the top, in England, that would mean your left wing, which means that green is the correct answer. If it's blue at the top, that would mean your right wing, and that means that the green is the correct answer. So that's quite remarkable. So that's 1, 2, 3, 4, 5. And I should say that's very impressive, given that there wasn't the opportunity for sort of consensual crosstalk or exchanging hypotheses amongst the audience, given it's online. Even more impressive, given that that's the quickest anybody has ever done it. So the only people I think who've managed to do it in 5 were an audience at MIT and an audience at Edinburgh University in the UK. So well done for that. That's very impressive. Okay, so remember that. It took you 5 data points to discover that rule. So the rest of the talk is really trying to understand how you were able to do that. That's an absolutely remarkable feat. So what we're going to do now is just rehearse the basic principles of active inference and self-evidencing, and then deploy those principles in the service of trying to simulate an artifact, trying to solve exactly the same problem. Right. So I normally start by asking another question, which I won't prolong the proceedings by asking you to answer, but I would normally ask the audience, if I were in person, imagine you're an owl and that you're hungry. What are you going to do? And then someone usually says, quite correctly, well, I'm going to search for my food. And they'd be absolutely right. So here's a predator searching for its food here. That answer holds many different important aspects when we ask the question, what kind of calculus or what kind of formalism would you use to explain good choices or optimal decisions? And I'm going to deliberately introduce a dialectic in terms of 2 different kinds of maths or calculus that one could use, and try and illustrate the differences. Later on, we're actually going to see that one is a special case of the other, but for the moment, I just want to contrast the 2. The first calculus, the first formal approach, would be to assume the existence of some value function of states of the world S at the next point in time that would ensue if I committed to some choice or action U at this point in time. And if this exists, then what I can do is I can always choose the decision that maximizes this value function of states, and that would give me a state action policy denoted by I of any given state at any given time here. However, that kind of formalism is not going to work given the answer, I'm going to search for my food. And the reason is that searching for food is all about reducing uncertainty. In this instance, uncertainty about where my food is located. But uncertainty is an attribute of a probability distribution or some sort of belief. And when I talk about beliefs in this presentation, I'm talking about Bayesian beliefs, conditional beliefs about states of the world, given some cues or sensory information or samples from that world. So that tells you something quite profound. It tells you that the best thing that you can do can't be a function of the states, but has to be a function of beliefs about the states, here denoted by Q of the states. So this Q denotes beliefs about the states, and this function actually turns into a function of a function. Another thing that the answer about searching for food gives you is the insight that the best thing to do at the moment depends upon what you know at this point in time. And therefore, the order matters. So, for example, it matters whether I try to search my food and then eat it, or whether I eat it and then try to search for it. They're going to have very, very different outcomes. So because of this sort of context sensitivity that unfolds through a process of belief updating or Bayesian belief updating on the basis of what happens if I do that, we have to introduce the notion of an optimal policy, a sequential policy that is a sequence of choices, and the good choices are going to be scored in terms of a path integral or a time average of this functional that I'm trying to optimize. Now, in general terms, a function of a probability distribution is usually a log of a probability distribution, or a potential or a value function from a physics perspective. So what we have here is a time or a path integral of an energy, a potential, which in physics is known as action. And if I can find the sequence of choices that maximizes this action here, then I've found the best policy and implicitly the best next move to make. And the reason I describe it like that is that one is very clearly appealing to do two very different kinds of principles when trying to formalize choice behavior. This kind of approach that rests upon beliefs about states rests upon Bellman's optimality principle, and some of you will be familiar with this in terms of underwriting optimal control theory, dynamic programming, deep reinforcement learning. If you're an economist, expected utility theory, Bayesian decision theory, and so on. Whereas this, in the sense that we are doing, trying to find a policy that maximizes an action from physics, a path integral of an energy. This appeals to Hamilton's principle of stationary action, and examples of this include the free energy principle, and as we will see, active inference, and it crucially accounts for the searching. So it accounts for artificial curiosity, sometimes known as intrinsic motivation, particularly in neurorobotics, and speaks more to the design principles that underwrite experimental design, getting the right kind of data that's going to resolve my uncertainty. We've already said that it pertains to sequential policy optimization in a setting of uncertainties, such as that afforded by partially observed Markov decision processes. So what's this universal energy function that I'm going to take the average of to give me my action so I can deploy the principle of stationary action? There's a long backstory to this that comes from the physics of self-organization. I'm just going to summarize it in terms of what it does and how we can understand it, both from the point of view of a statistician, but also from the point of view of a psychologist or a behavioral scientist. So this is the overall architecture. We've got a brain here, or some decision-making artifact that is embedded in some environment, and it exchanges with the environment by sampling sensory states, that are caused by the external states exterior to the brain in this instance. These observations, these outcomes are then used to infer the states of the world that cannot be seen directly, but are only inferred on the basis of cues or observations or outcomes. And this, we will see, provides an optimal, base-optimal inference, a belief about states of the world. And this rests upon standard variational Bayes that effectively maximizes a bound on the marginal likelihood or the evidence for a particular model and implicit beliefs about the world. It's a kind of technology that you implicitly use whenever you're doing a t-test. It is exactly the objective function used in state-of-the-art deep learning that uses variational autoencoders, for example, also known as an evidence lower bound or an elbow. From a statistician's point of view, the belief is going to essentially minimize the complexity while providing an accurate account of what's going on, an accurate account of the observed data. So I've just written that down formally here in terms of the accuracy. Under my beliefs, the accuracies are going to maximize the log probability of some observations given some beliefs, and that, for example, would be minimizing the residual sum of squares in a general linear model, for example. This is the goodness of fit, the accuracy. And this bound here, this variation-free energy here, is equipped with another really important term that can be understood as complexity. So this is just the scoring, the degree to which I change my mind on seeing some observations. Mathematically, it's a KR divergence between my posterior beliefs, after seeing the observations, and my prior beliefs before I see the observations. So it scores the information gain, literally the amount to which my prior beliefs are updated or are moved by seeing some data, the degrees of freedom I'm using up in my belief updating to provide an informed and inferred account that is as accurate as possible. And by optimizing this mixture, we get the best beliefs about unobservable states outside. However, that's not sufficient in order to determine how I'm going to get those data by actively sampling the world through my decisions and my actions to generate the data that I'm trying to use to infer what's going on. So what's that functional I referred to before that we're going to take the path integral of? Well, it's very simple. It's just that if I'm trying to maximize my free energy, then I'm going to choose those actions that maximize the expected free energy if I chose that course of action. And what's that? Then I'm going to condition this upon the policy pi here. So what does that look like? Well, it's very simple. I'm just going to take the expected complexity and the expected accuracy and see what that unpacks as. So the expected complexity is just basically the difference between what I anticipate will happen if I commit to this course of action or this policy here, and what a priori I expect to happen. So it's just the risk of departing from my prior preferences, the kinds of state that characterize me that I would prefer to occupy. And this is also foundational in things like optimal control theory in the form of KL control. It's also can be one way of reading risk-sensitive control in economics. The inaccuracy or the negative accuracy when averaged or when we take the expectation becomes ambiguity, basically an attempt to sample those data that are minimally ambiguous in the sense that they provide definitive, precise information. So for example, if I went into a dark room, I would switch on the light to ensure that my visual sensations were unambiguous in terms of disclosing the likely causes of my sensations. So that means the imperatives for this kind of good behavior have this pragmatic risk-reducing aspect and this more epistemic ambiguity-reducing aspect. I've just written out the equations in full here just to sort of unpack this expected free energy in relation to the free energy here. If you don't like the maths, then don't worry about it. I'm just using these equations iconically just to illustrate a beautiful symmetry or invariance as we move from the objective functions or the imperatives for sense making, say perceptual inference, to examine the foundational nature of action and planning as inference in the spirit of policy selection. So here's the decomposition I've just described in terms of a mixture of complexity and accuracy. Just to note that we can just rearrange a couple of these terms and express it in terms of this evidence lower bound, the log evidence being the log of the probability of my outcomes given my model of those outcomes or data. And this term, because it's another KL divergence, can never be less than 0. And that's why it's called the mixture of the log evidence and the bound is known as an evidence lower bound here. So it's just another way of interpreting the mixture of accuracy and complexity. And these are the equivalent expressions for the same quantities expected in the future. So we've just said that complexity becomes risk, inaccuracy becomes ambiguity. And interestingly, this bound here becomes something we call intrinsic value, and this log evidence now becomes extrinsic value. So what do I mean by that? Well, let's just examine some special cases. Let's first of all ignore the extrinsic value, ignore my prior preferences. A priori, I'm happy to sample anything. And that leaves us with this term here, that is a KL divergence, an expected KL divergence between my beliefs about the unobservable states of the world. If I had access to the observations that would ensue under a particular policy relative to the same beliefs without the observations. So this again is an information gain, but in this instance, it's an expected information gain that I want to maximize. So in the visual search literature, this would be known as Bayesian surprise. More generally, it's just the mutual information between causes and consequences. The external causes producing the sensory consequences I would expect given a particular policy. Let's take a degree of uncertainty off the table. In fact, let's just remove the ambiguity. Let's say that the lights are shining brightly and every observable state of the world can now be observed directly. So there's no uncertainty about the states given my observations. And that just leaves this term here, which is the risk we've just been talking about. And as I mentioned before, this can be read as KL optimal control or risk sensitive control, in which we're simply trying to minimize the divergence between our prior beliefs about either states of the world or my observations, and that which I anticipate if I roll out into the future under this particular policy. Let me take the last kind of uncertainty away and assume that there is no more intrinsic value or epistemic affordance or unknowns that I can resolve through exploring my world. And I'm just left now with this extrinsic value, this expected log evidence. And that's just basically the expected log of my prior preferences, either about observations or about states of affairs in the world. And this, of course, can be read as expected value or expected utility in economics, or reward, expected reward in behavioral reinforcement learning. And the key thing that this slide is trying to intimate is that we've derived now the the calculus or the formulation of good behavior that we would have had we chosen Bellman's optimality principle. So by taking uncertainty off the table, I've converted a generic problem that will be solved through maximizing this expected free energy into a more classical problem where that is a special case that just is maximizing expected value, actively realizing my preferred outcomes. So that's the basic story in terms of Bayes' optimality. So this is beyond Bayes' optimal assumptions about perception and sense making. It takes us into the notion of an actor under uncertainty being optimal, and being optimal in two senses. First of all, making Bayes' optimal decisions in the spirit of maximizing expected value, where value is a log of my preferred outcomes, but also being Bayes' optimal in the spirit of optimal experimental design, actively soliciting data that reduces my uncertainty about the hypotheses I have about the way that those data were generated. Technically, this is done by maximizing the expected information gain. And together, the expected value and the expected information gain are just equal to the expected free energy. So that's the basic maths. What I want to do now is briefly introduce the kinds of simulations and their behavior that we use to illustrate the behaviors and the sense making that emerge under this view of Bayes' optimal action. And then we're going to use those simulations to try and solve the problem that you solved at the beginning. So generally for most, if you like, decision theoretical, behavioral or psychological simulations, we use a partially observed Markov decision process, which is actually very simple and very generic. So again, ignore the equations over here, just focus on this graphic here. So what we're talking about here is a generative model that has the evidence, if you like. So when we're talking about free energy as an evidence lower bound, what is the evidence for? Well, it's the evidence inherent in some data for a particular model, a particular set of beliefs about how those data were generated. And that's just a generative model. And it just requires you to write down formally the probability distribution over causes and consequences here, states of the world, and the consequences, the observable outcomes here. So we do this in time, where states unfold as time goes on, and each state at each point in time generates an outcome. The probabilistic mapping between the causes and the consequences is the likelihood part of the generative model, usually in my world denoted by a big tensor A. The states evolve in a way that depends upon the policy. So the way that the world changes depends upon how I intervene on that world or act upon that world. And those transitions from one state to the next state depend upon a probability transition matrix that constitutes the priors of my generative model, framed in terms of the unknown random variables, which are these unknown states of the world. That in turn depends upon the policy, and we've just said that the policy depends upon our preferences, usually denoted by a cost function or a vector of preferred or anti-preferred outcomes that gets into my policy via the expected free energy here. We also have to equip this model with prior beliefs about the initial states and some hyperparameters that control the precision. So that's the model. A very simple, very generic kind of model that can handle most discrete cases that people deal with in an empirical setting. These are the equations that just say what I've said mathematically. And then having written down the model, we know the functional form of our beliefs and the implicit belief updating. The belief updating really is very simply changing the approximate posterior, that Q, in order to maximize the free energy F, and then selecting a policy that maximizes the expected free energy given my cue that I've used to make sense of the data. Again, I repeat, this kind of Bayesian belief updating is fairly straightforward using off-the-shelf mathematics, and indeed nowadays software that you can get from GitHub or other open source libraries. The nice thing from the point of view of a neurobiologist or a psychologist is that there's the functional form of this belief updating very, very similar to the processes that we actually study, certainly in cognitive neuroscience and in imaging neuroscience. So what are we updating beliefs about? Well, there's only two things that we don't know: states of the world out there and what we're going to do next, namely the states and the policies. I've actually added in one of these precision parameters here for people who like dopamine. But the key ones are these two things here. And updating beliefs about states of the world is very simple. It just takes the current evidence from our outcomes and ensures a priori that is consistent with beliefs about the previous state of the world and states of the world in the future under a given policy. And we just mix these messages or sources of evidence together, apply a softmax function to get a distribution over the expected state of the world at the next time point or the current time point. So this looks very much like the kind of equations you'd find in neural mass modeling. We're just taking a voltage, current, or some nonlinear function or some linear mixture of representations or activities elsewhere in a brain, and these become connectivity matrices. So we can now read the optimization of the parameters of the model, the likelihood and the priors, basically as learning or changing connection strengths in the brain. Policy selection is just a straightforward standard softmax policy rule predicated on the expected free energy. We've added a softmax parameter or precision parameter here that when estimated, its inverse becomes beta, and this behaves very much like a reward prediction error of the kind used to understand dopamine discharges in many empirical studies. I've just said that updating the connections and the parameters of the generative model just looks like learning. And if I just work out the belief updates for the parameters, the learning, then we get something that looks formally identical to associative plasticity with an associative term and a decay term denoted by this expression here. This is just for the initial states. Similar expressions exist for the A's and B's here. And then finally, action selection is choosing that action from the most likely policy that I've inferred to commit to and to act upon at the next time step. And then you can play all sorts of games about, which parts of the brain and do these different aspects of belief updating and or learning. Here's a crude example, putting the hippocampus in charge of building beliefs over time about unfolding states of affairs out there. Here's an example that I just briefly want to show you, illustrating a fundamental aspect of this kind or this account of sentient behavior. It is very simple. It's just predicated on a two-step maze task where the synthetic mouse can make two moves. And the idea is that the mouse wants to locate a preferred reward, the red stimulus here, that could be on the left or the right-hand side. Because the mouse only has two moves and doesn't know whether it's on the right or the left, and once the mouse enters the right or the left arms, it has to stay there, it can either take a chance and go and one or the other arm and either spend two moves with its reward or no moves with its reward, so a 50-50 split. However, in this paradigm, we have introduced a twist. We've given the mouse another choice. It can use its first move to go and look at an instructional cue that tells it where the reward is. So now it can use up one of the moves to resolve uncertainty and then go and secure its reward with a degree of confidence and stay with it for the remaining move. So on average, again, exactly 50% of the time it will spend with its reward. So from the point of view of the Bellman optimality principle, these two behaviors are identical. But from the point of view of the epistemic affordance afforded by that instructional cue, that will maximize expected information gain or resolve the most uncertainty. The implicit salience means that this synthetic rat will always commit to the epistemic policy and should in principle always go and secure its food. These graphics and equations just show you how you would write down this generative model. It's incredibly simple. There are tutorials on GitHub now telling you how to do this.
Karl, can I use my prerogative to just ask a quick question?
Yes, of course.
Slipped in just 2 minutes ago, you slipped in the word when you started talking about the synthetic rat, the word sentient, and I wanted to know why you said that.
I'm using it in the sense of sentient behavior. So there are two jobs that I often have to do. I'm either talking to people who do psychophysics and perception and say, well, yeah, that's an important aspect, but there's another side of the coin, which is the fact that the data, the sensations that you're trying to make sense of have to be actively solicited. So that's where active inference comes from. But for people in control theory and people who are focused on, say, reward maximization or machine learning, you have to say, yes, that's fine, but you also have to do your state estimation. You also have to infer and resolve uncertainty about states of the world that you're trying to control and act upon. So generally, we use the word either active inference or sentient behavior just to try and get both in the mix there. So the word sentient here is used in a very technical and its original sense to imply sense making or sensation that is not meant to induce thinking or reasoning. Does that make sense?
Yes, we'll take it up again in questions, I think.
So yes, I was saying the actual functional form of this of these models is very simple, and here are the choice behaviors that ensue when you just integrate these simulations to try and reproduce the kind of behavior that we want to try and explain. What I've done here is just show the results from 32 trials, each starting with the reward on the right or the left, and here showing the policy that was chosen by the rat at each point. The policy, there are only a handful of policies that can either stay there and go down, or can go to the right and stay there, or it can go to the bottom and then go to the left. And it has to choose which policy, namely 2 moves, to make at each point in time. And what we see is, and I should just say that these are the final outcomes, and this is the expected prior preference or reward here, which is always negative by construction. And these are the hidden states, which in this instance were the context in which the animal started. Was the reward on the right or was it on the left? And as we might expect, on the very first move, the rat engages in this response to the epistemic affordance of the instructional cue and goes and gets its reward here. Now, we played a trick on this mouse by leaving the reward on the left-hand side after the first few trials. And that meant, as time goes on, the mouse learns that the context is such that the reward is always on the left-hand side. And in turn, that means that there's less and less epistemic value and information gain in going to the instructional cue. The mouse learns nothing after a certain period of time because it knows where the reward will be. And at some point, the pragmatic or the extrinsic value of going directly to secure the reward becomes greater than the epistemic affordance of going to the instructional queue. And you get this systematic and discrete switch of behavior from exploration to exploitation here at around 20 moves here, where the rat will go directly to its reward and spend 2 moves sitting on the reward. And this is a fundamental and almost universal behavior under uncertainty, that there's this systematic exploration under constraints, namely that you avoid very non-preferred outcomes, until enough novelty has been used up and has been removed, or salience has been removed, so that you are now confident, sufficiently confident to invest and leverage your prior preferences and start to forage. So that's the basic behavior. What I want to do now is to close by coming back to our task and now trying to simulate an agent using exactly those equations and that belief updating scheme, using but now applied to the task. So if you remember, we had to choose what the correct color is. To model this task, we have to drill down into the details and to the level of specifying particular actions that would cause the synthetic agent to look at one particular clue or another particular clue, and when they think that they know what the rule or the correct color is, then to actually use their, in this example, their saccadic eye movements or their gaze to identify the correct color. So how on earth do we build a model of this seemingly complicated world? It's actually much simpler than you might expect. You just have to write down all the latent or the hidden states that will be necessary to generate outcomes. So we just need to know what is the rule. Is the correct color on the left, in the center, or on the right hand side? What is the correct color? Where am I looking? And what choice have I currently committed to, or have I not yet chosen? And with all of these hidden states, I can generate what any agent would sense in terms of what they are currently looking at and how they are and what feedback or outcomes they receive, the correct or incorrect, or they haven't yet chosen, where they're looking and what they're actually, where they're sensing themselves to be looking and what they're actually seeing. And all the interesting contingencies and causal structure in this world that has yet to be discovered or learned can be encoded in this likelihood tensor that I've tried to sort of unpack here. And again, it looks a bit complicated, but it's very, very simple. All that we're saying here is that if the rule is on the right, then the color at the center, if I was looking at the center, must be, sorry, if the rule is on, the correct color is on the left, then the color of the center must be red. And if I'm looking at the left in this context where the correct color is on the left, then the color I see is the correct color. So there's a precise mapping between what I see and what the correct color is that is very context sensitive, and that context is the rule, and the rule declares itself by the color of the center stimulus. And I have to scout around and look for this information and hopefully discover the rule. And once I know the rule, I know what the correct color is and I know how to respond. However, I don't know the rule. I start off with your priors that the color of the center denotes the rule in question, but I have no idea what the rule is. And so everything else I have flat or uninformative priors about. So I don't know how to respond. I don't know how to choose because I have not yet discovered or learned this structured mapping that will allow me to make precise decisions. So what happens when we put that that scheme, that active inference scheme, into play with this particular generative model? Well, this is what happens. Again, using the same format, these are the initial states and the policy selection in terms of the sequence of eye movements I make, scouting around, looking at the colors of different hues, and then looking at the choice circles to declare my choice. And this is the final outcome and the performance here scored in terms of the free energy here, the negative free energy, and the accompanying confidence I have about the choices that I have made. And what we see, and I should say that the performance here means that black is a correct choice and red is an incorrect choice. So very much like we were seeing when we were playing this game, it takes many, many moves, many games before there is a consistently high and correct performance that is accompanied by a decrease in the negative free energy here, that is also accompanied by an increase in the confidence that this synthetic agent has about its policies. So that's nice. It affords the opportunity to do all sorts of interesting things. So for example, I can now look at the belief updating expressed in terms of simulated neural activity in response to exactly the same stimuli, but in situations where I'm completely ignorant about the causal structure, and when I know the significance and the meaning of that cue, because I've discovered the contingencies and the rules that underwrite the way in which my outcomes are generated. So just taking these two points highlights the difference between the context in which I am now making my decisions, making my moves. Here I have good inferences that are held with confidence. But the question now is, why would I look anywhere? You know, at the beginning, if the consequences of action had no meaning, how could anything resolve any uncertainty? If I don't know all those contingencies, what uncertainty is there to resolve? And this graphic is meant to illustrate where that source of uncertainty resolution comes from. So here's exactly the same unpacking of all these equations that we had previously with the free energy here underwriting our belief updating about hidden states, and then feeding into our evaluation of the goodness of a policy in terms of the expected free energy, minimizing risk and ambiguity. But what we've done here is just unpack that by noting that not only are the states unknown, but also the parameters are unknown. And therefore the information gain associated with resolving uncertainty about the states also plays a profound role when applied to the parameters. And that epistemic affordance we call novelty. So as opposed to the salience of looking over there or opening this door, the same kind of epistemic affordance emerges when we're talking about the very structure of the contingencies and the laws and the rules embodied in this instance, the likelihood matrix. So this is a mathematical description of novelty, and it rests upon learning. So in exactly the same way that we have our belief updating about states, we have our belief updating about the parameters, the connectivity weights, if you like, that is driven in exactly the same way to minimize complexity and accuracy, and also underwrites, or the ability to learn underwrites now the ability to respond to novelty. So just summarizing that, what we now have is if you like, a generalization of this expected free energy that previously entertained this extrinsic value or utility, this intrinsic value or epistemic affordance or salience, and we're now supplementing it in the context of learning with novelty. So put very simply, that provides a Bayesian formulation of the way that we are compelled to find out what would happen if I did that. So I want to close now with the very final kind of optimization that goes beyond actively optimizing the way that we learn, basically actively inferring how to learn by getting the best kind of data so that we enable that learning by responding to novelty. What I want to do now is just to remind you that this synthetic agent took about 15 exposures before it had a resemblance of, if you like, insight, or behaved as if it started to learn the contingencies or the rule. You, on the other hand, in fact, I should move the arrow down to 5, were able to do it after 5. So that's what I meant by what you did was mathematically impossible. What you've done is beyond a Bayes optimal inference and learning. So how were you able to do that? The trick I think that you were using implicitly lies in these expressions here. Previously, we're talking about learning as minimizing complexity by changing beliefs about the likelihood tensor, basically changing connection strengths in the right kind of way. But notice we can also minimize or maximize this evidence lower bound here, not by changing the posterior beliefs, the connectivity, but by changing the prior itself, by making the prior more like our posterior, by revising our beliefs about the very structure of the model, namely structure learning. And what this basically means is that I can go in with a series of hypotheses and ask, if I'd use this prior belief and compare it using this KR divergence to my posterior belief, would I have optimized my free energy? In other words, would this have been a better prior belief to start with? And I can scroll through now all sorts of hypotheses about the nature and the form of the rules and evaluate, and in fact here there are about 64, evaluate them in relation to my posterior beliefs after accruing a certain amount of data, and then score the goodness of these alternative hypotheses in terms of their contribution to this evidence lower bound. And you may be asking, well, why do I think that you were doing that? Well, one reason I think you were doing that is I think we all do that. So for example, during sleep, some people believe, during wakefulness, some people believe that our parameter learning is evinced through experience-dependent plasticity or associative plasticity, so that we spend our eyes open, actively engaged with the world, state of mind, behavior, accruing and assimilating associations and connectivity and regularities literally in our synaptic connections. And then when we go to sleep and there are no more data or observations to explain, we're just left with a complexity term. And one way to minimize the complexity is to regress or remove those redundant parameters, or if you're a biologist, synaptic connections. And this, some people have referred to as synaptic regression, people like Giulio Tononi in sleep research. And that's the basic idea, that we spend a lot of time getting data and making associations and having an overly expressive, overly parameterized generative model. And then we ignore the data and have a period of introspection or sleep or thinking about things, and then minimize the complexity by removing the redundant connections, all in the service of optimizing this free energy functional of different unknowns. And in this instance, it's unknowns about the structure of the likelihood mapping itself. And so when we equip this agent with the ability to just introspect and to have a little nap between trials, then we can massively improve its ability to recognize the rule via this process of structure learning, at which point it realizes what the rule is by comparing the different hypotheses. So this just sketches out the true likelihood, the prior beliefs, and the posteriors after about 12 moves in this instance, with and without the ability to sleep. And these are the final results I'll show here, where we repeated this experiment with 64 synthetic agents and just recorded the point at which they realized the rule, realized in a discrete way, because they suddenly replaced their old priors with new priors on the basis of the posteriors that they had accumulated by sampling 1, 2, 3, 4, 5 up into 32 trials. And what we see here is the performance of the agent stays optimal, in noting that these were sort of randomly generated cues, emulating the performance that you were able to aspire to under Zoom pressure, namely about 5 instances is sufficient if you have this kind of Bayesian model reduction or structure learning as part of your optimal foraging. So, in summary, sources of uncertainty, how it's resolved, and the equivalent epistemic affordances. We can have uncertainty about states. We resolve that by Hanninger's inference and inferring, and that looks as if we're seeking out salient information. Uncertainty about parameters or contingencies is resolved by learning parameters, and the epistemic or the affordance aspect would emerge as novelty. And then uncertainty about the generative model itself is resolved through this process of offline structure learning. That can be, if you like, read as discovery or knowledge, ingraining knowledge or distilling knowledge from what we've acquired through responding to salience and novelty. And that may be one reason for minimizing complexity during sleep. So to close, simplicity and accuracy is equal to evidence. Everything should be made as simple as possible, but not simpler. And with that, I will close. It only remains for me to thank those people whose ideas I've been talking about, and of course, to thank you for your attention. Thank you very much indeed.